everyone, a warm welcome to the second part of complex integration by Cauchy's integral formula for derivative. I explain how to apply Cauchy's integral formula for derivative in part 1 and its link is. So before watching this video, you have to watch this video. Cauchy's integral formula for derivative is integral over c f z by z minus z naught raised to n plus 1 dz is 2 pi I by n factorial fn of z naught, where this fn of z naught is the nth derivative of f at z naught. Here fz is an analytic function within and on a simple closed curve C, and z naught is a point within C. So for applying integral formula for derivative, we have to choose z naught, n and fz. Then for getting the value of the integral, you have to multiply fn z naught by 2 pi I by n factorial. In certain questions, there is one and only one singularity within C. But in some other integrals, you can see there may be more than one singularity within C. But we can apply this result only for exactly one singularity within C. In this video, I am going to illustrate how to apply Cauchy's integral formula for derivative for the evaluation of complex integrals with exactly one singular point within C. Let me illustrate it. Consider the integral over c e raised to z by z square plus 4 b z minus 1 the whole square dz, where c is mod z minus 1 equal to 2. First you identify its singularities. Clearly its singularities are 2i minus 2i and 1. Among these three singularities, 1 is the only pole of the given function which lies inside of C. Both the 2i and minus 2i are outside of C. Here we have to apply Cauchy's integral formula for derivative because here 1 is the singularity of the given function which lies within C, and the corresponding part is z minus 1 the whole square. It is with a power 2. If the power of z minus 1 is 2, we can evaluate this integral only with the help of Cauchy's integral formula for derivative. And Cauchy's integral formula for derivative is integral over c f z by z minus z naught raised to n plus 1 dz is 2 pi I by n factorial nth derivative of f at z naught. See, the difference between Cauchy's integral formula and integral formula for derivative is, in the integral formula, the power of z minus z naught is 1. If the power is not equal to 1, then you have to apply Cauchy's integral formula for derivative. So for evaluating this integral, we have to identify three terms, and the three terms are z naught, fz and n. If you can identify these three, then you can give the integral as 2 pi I into nth derivative of f at z naught divided by n factorial. So let me illustrate how to integrate this with the help of Cauchy's integral formula for derivative. Here we have to choose z naught. See, in Cauchy's integral formula for derivative and in Cauchy's integral formula, z naught is always the singularity of the given function which lies within C. So here 1 is the singular point which lies within C, so you have to choose z naught as 1. You look at the given function, its power is 2. So you have to choose n as 1. Then fz is the remaining portion of the singular part which lies within C. That is, you consider z minus 1 the whole square, and the remaining function you have to choose it as fz. So the suitable fz here is e raised to z by z square plus 4. Next, by integral formula for derivative, integral over c fz by z minus z naught raised to n plus 1 dz is 2 pi I by n factorial fn at z naught. Here n is 1, so f dash z naught is 1 by 1 factorial. We have to find f dash 1. For that, you find f dash z. See, fz is a quotient, so you apply quotient rule. Quotient rule, z square plus 4 the whole square upon z square plus 4 into e raised to z minus e raised to z into 2z. Really there is no need of simplifying this. You can directly put z equal to 1. So f dash 1 is 5e minus 2e by 5 square. That is 3e by 25. That is 6 sin pi by 25. So if you replace fz by e raised to z by z square plus 4 and z naught by 1 and n by 1, you can see this is our given integral. So we can conclude the value of the given integral is 6 sin pi by 25. Next, consider another interesting question. Integral over c z by z square plus 4 the whole square dz, where c is mod z plus 2i is equal to 1. You identify its singularities. Its singularities are 2i and minus 2i. So we can factorize the given function as z by z plus 2i into z minus 2i the whole square. That is z by z plus 2i the whole square into z minus 2i the whole square. See, this is our given function. Given function is this one. We have to evaluate integral over c z by z plus 2i the whole square into z minus 2i the whole square dz. Clearly, minus 2i is inside. But 2i, when you put 2i, it is mod 4i, it is 4, which is greater than 1, so this is outside. Here, the only singularity which lies within C is minus 2i and the corresponding part is this part. See, the inside singularity should be taken as z naught. So, z naught is minus 2i. And its part is with power 2. So, you have to choose n equal to 1. See, the equation, it is n plus 1. So, you consider n plus 1 as 2. So, what is n? N is 1. Next, we have to identify f with z. See, this is its corresponding part. So, you have to choose this as f with z. So, f with z is z by z minus 2i the whole square. We have by Cauchy's integral formula for derivative. Integral over c f z by z minus z naught raised to n plus 1 dz is equal to 2 pi I fn at z naught by n factorial. Here it is 2 pi I f dash of minus 2i by 1 factorial. That is 2 pi I f dash minus 2i. Next, we have to find f dash z. See, this is f z. So, what is f dash z? F dash z is denominator square upon denominator into derivative of the numerator minus z into 2 into z minus 2i. You can remove an z minus 2i. Here z minus 2i, here you can see an z minus 2i. So, there is an z minus 2i is common in the numerator. You cancel with the denominator. So, you can see the denominator is z minus 2i the whole cube. Z minus 2i minus 2z. That is minus 2i minus z by z minus 2i the whole cube. So, what is f dash minus 2i? F dash minus 2i is minus 2i plus 2i divided. See, the numerator is 0. Whatever be the denominator, the answer is 0. So, you put it here, you can see the answer is 0. Look at another interesting question. Integral over c z square by 2z minus 1 the whole square dz, where c is mod z equal to 1. First, we have to identify its singularity. Clearly, it has only one singularity and which is half. It lies within c. So, you have to choose z naught as half. See, our Cauchy's integral formula is integral over c f z by z minus z naught raised to n plus 1. See, the denominator is z minus z naught raised to n plus 1. So, here it should be z minus half the whole square. So, you have to keep the denominator like this. Also, you have to notice that In Cauchy's integral formula for derivative, the coefficient of z must be 1. So you have to keep the coefficient of z as 1. So integral over c, z square by, you take 2 outside, then 4 into z minus half the whole square. Now it's ready for applying the Cauchy's integral formula for derivative. Our singularity is half and its power is 2. If it is 1, you apply integral formula. If its power is greater than 1, we have to apply integral formula for derivative. So we have to choose z0, that is half, n is 1, you just less 1 from this 2, that is n. F is z, what is f is z square by 4. Then by Cauchy's integral formula, answer is given by 2 pi I by n factorial, fn is z0. That is 2 pi I f dash of half by 1 factorial. Next we have to find f dash is z. What is f dash is z? It is 2z by 4, that is z by 2. What is f dash half? You put z equal to half. So the answer is 1 by 4. Here you put f dash half, that is 1 by 4. So the answer is I pi by 2. So the value of the given integral is I pi by 2. Next we have to evaluate the integral. Integral over c, 3z minus 1 by z cube minus z dz. First along c mod z equal to half. Next we have to integrate along the circle mod z equal to 2. First you notice its singularities. Singularities are clearly the singularities are 0, 1, minus 1. You consider the first circle, that is mod is equal to half. In the first circle, only 0 is inside. 1 minus 1 are outside of C. Next, we have to factorize the given function. See, the given function can be factorized like z into z minus 1 into z plus 1. See, the inside singularity, that is, it is here. So, we have to choose z0 as 0. Inside singularity is always z0. So, we have to keep z0 as 0. And its power is 1. So, here there is no need of applying Cauchy's integral formula for derivative. So, you can apply this only for its power is greater than 1. If the power is 1, the result is Cauchy's integral formula. Simply integral formula. So, in integral formula, we have to keep z0 and f. So, what is f? F is this part. So, you have to keep f is set as 3z minus 1 by z minus 1 into z plus 1. What is Cauchy's integral formula? Integral formula is integral over c f is set by z minus z0 dz equal to, see, in integral formula for derivative there is n plus 1. See, in integral formula it is raised to 1 and the answer is 2 pi I f of z0. I just discussed this question here because to distinguish the difference between Cauchy's integral formula and integral formula for derivative. It is 2 pi I into f of x z0 is 0, f0. So we have to find f0. What is f0? You put z equal to 0 here. f0 is minus 1 by minus 1, that is 1. So answer is 2 pi I. See, the given function is factorized like this. Corresponding singularities with power 1. So we have to apply only Cauchy's integral formula. If its power is 1, the only result is Cauchy's integral formula and it is given by integral over c f is set by z minus z0 dz equal to 2 pi I f of z0. Here, 3 singularities are within C. Already we noticed that if more than one singularity lie within C, we have to start with partial fraction. So here also we have to start with partial fraction. So give the partial fraction for 1 by z into z minus 1 into z plus 1. and its partial fraction is a by z plus b by z minus 1 plus c by z plus 1. See, the numerator of z can be found by putting z equal to 0 here, that is 1 by minus 1 into 1, that is minus 1. So a is minus 1. For getting b, you put z equal to 1 here. So 1 by 1 into 2, it is 1 by 2. For getting c, you put z equal to minus 1 here. So 1 by minus 1 into minus 2, that is 1 by 2. See, this is the partial fraction of this term. You have to evaluate this integral. So you have to multiply throughout by 3z minus 1. Next, you integrate on both sides from over c. See, in the right side, integral of sum, that is sum of the integrals. So you split the integral. Let it be I1 plus I2 plus I3. That is equation number 1. Next, we have to find I1, I2, I3. Evaluation of I1. So I1 is integral over c. You can take the negative to the inside. So integral becomes 1 minus 3z by z into dz. Here we have to apply Cauchy's integral formula. So we have to choose z naught as 0 and fz as 1 minus 3z. So by Cauchy's integral formula, 2 pi I f of z naught. Here z naught is 0. What is f0? F0 is 1. So from here f0 is 1. So the answer is 2 pi. So we have I1 is 2 pi I plus, next we have to evaluate I2. I2 is integral over c half 3z minus 1 by z minus 1 dz. Here the inside singularity is 1, so you have to keep z naught as 1. Here clearly fz is half 3z minus 1. So integral over c, fz by z minus z naught dz is 2 pi I f of z naught. Here z naught is 1, so f of 1. We have to find f of 1. What is f1? f1 is half into 2, that is 1. So I2 is 2 pi I. Next we have to find I3. What is I3? Integral over c half 3z minus 1 by z plus 1 dz. Here the inside singularity is minus 1, so you take it as z naught. And the remaining portion as fz, that is half into 3z minus 1. By Cauchy's integral formula, integral over c fz dz fz by z minus z naught dz is 2 pi I f of z naught. Here 2 pi I f of minus 1. So for getting f of minus 1, you put z equal to minus 1 here, that is half into minus 4, it is minus 2. So you put f of minus 1 as minus 2, you can see the answer is minus 4 pi I. Alright, I3 is minus 4 pi I. So it is 0. So given integral is 0 along mod z equal